Hi, everybody. Welcome to Love Goes Live. My name is Mark Lupkwitz. I'm a molecular biology professor at St. Michael's College, and I've been making videos on COVID-19 and other sciencey stuff, really for the general public as well as for my molecular genetics students. And if you happen to have read the New York Times today, there was an article that really caught my attention. And the article is about how the strain of COVID-19 that is going around the East Coast, and particularly in New York City, seems to have originated from Europe. And the scientists that came up with this conclusion got their data from a website called nextstrain.org. And I happen to follow that website, and the science is so fascinating. So I thought I'd take the opportunity to go over the science with you all today. So without any further ado, let's look at some science. All right. A little bit of a review here. If you've seen some previous Love Goes Lives, you've seen this before, but I want to really just go over this idea of copying genetic material and how when you copy it at some frequency, not at a high frequency, but there are changes / mutations that are introduced, and you can use that to trace origin. So let's just pretend like we have a sentence here that says, Mark Lupkwitz is a biology professor at St. Michael's College. So that would be genetic material. And when it gets copied at some frequency, errors are going to be made, mistakes, right? Copy the mistakes, and you get more errors and more errors, more errors, and more errors. Now, a point that I want to make here is if you look at relatedness, let me get an annotation tool here. So if you look at this bottom phrase, it is most similar to that phrase, and it's second most similar to that one, and it's most distant from the original. So by tracking the changes, you can come up with sort of a lineage of who is derived from who. Okay. Give me a second here to clear some annotation tools, and let's go on to the next slide. So as you guys all know, COVID is not made up of the alphabet. It's actually made up of ribonucleotides. It's a single strand of RNA virus. It has about 28,000, a little north of 28,000 nucleotides. And those are A, U, C's, and G's. So I have a very short sequence here. And I've underlined just one of the nucleotides. That would be that U. Okay, so you can imagine if we were to pretend like this was a viral genome and we were to copy it, let's say that there's an error that's introduced, and now we have two variants within the population. And so we could say, like, this one hasn't gone away, it's still circulating within the population, but now we have a second variant that's circulating within the population. Now, I'm not calling them strains because I'm not really sure at what point virologists say variant versus an actual strain, but they are slightly different at this point. And then if we were to copy the genetic material again, notice that the original is still in the population. Like, this guy hasn't gone anywhere, but now we've added a third one. So we have 1, 2, 3 different viral strains / variants that are circulating within the population. And then if we were to do this experiment one more time, now we have even another one. But I want you to notice, and this is probably the most important thing I'm going to say on this image, is that this final product right here is most divergent from this one over here. Okay, they went through different paths to get there. And if you were to just draw out the tree, the relatedness, this one at the bottom and this other one at the bottom are the most distantly related. Remember that. That's probably the take-home message for this whole slide. Okay, so what do you do with that sort of information? So you're sequencing RNA genomes that you're pulling out of individuals that have been infected with COVID-19. And what scientists do is they make a tree, a family tree. It's actually called a phylogenetic tree, but it's a tree of relatedness. And so if you look at these 3 siblings right here, right? They are very closely related. And what you want to do is you want to ask the question, how far well, they have this common node right here. And these two are much more related than they are to their cousins. And notice that I drew this long line along these branches. So the branch length matters. So the longer the branch length, the less similar or the least related you are. So that's the big take-home message. When you look at a family tree, or if you look at a phylogenetic tree, you're really looking at branch length. What's the distance between 2 nodes, 2 individuals, or in our case, what's the branch length between 2 strains of COVID-19? That tells you relatedness. All right, let's go to the next image here, and I'm going to show you what some of this data actually looks like. All right, so I pulled this off of, and let me move my little picture of myself here. I don't know if you guys can actually see that. I'm going to put myself over here. So this is actually a phylogenetic tree as of today, which is what, April 9th of COVID-19. Each dot represents, if we were to just look at one of these dots right here, each dot represents a clinical isolate that was sequenced of COVID-19. And let's look at these two right here. So the branch length between those two green dots is not very far. So those two isolates are really, really similar to each other. Now, the original COVID-19, the first one, is all the way over here to the left. So that's the original COVID-19 that came out of a bat, went into a human, and then you notice it started diverging. And if you notice within this tree, there's a couple of really big branches. But I want you to focus, first of all, well, let me tell you what the color means. So the color purple represents Asia, specifically China, right? So the origin here started in Wuhan, and then you notice there was some divergence. The red dots are North America. So here's the first thing I want you to notice. There's a big cluster of red dots down here, and these are sequences and isolates that are coming from the West Coast. This other cluster of red dots is actually from the East Coast, all right? Now remember that the length of the branch matters. So if we just were to draw the length of the branch, right, and trace this all the way to here, whoops, I jumped there. Notice that the strain or the variant of COVID that's running around the West Coast is actually very different than the one that's on the East Coast. And if you were to ask the question, starting with the West Coast again, so let's just look at this population down here. It is most similar to these purple dots, which suggests, in fact, I think now it's pretty well widely accepted, that the COVID-19 that started in Washington on the West Coast originated from Wuhan. But here's what came out in the New York Times today. If you look up here at the strains that are in New York City, they are most closely related to these green dots. Those are isolates that are from Europe. So this shows, if you notice the branch length, this shows that the strain that is in New York City is most similar to the strain that is in Europe, which implies that it originated from Europe. Now here's what we all want to know. Here is like the million-dollar question. Does it matter clinically, right? So there are two very different, or not, I don't know if they're very different, but there are two divergent strains of COVID-19 in the United States right now. One which is prevalent in the East Coast, most commonly related to, or most similar to the one that's in Europe, and then one that's on the West Coast, which is most similar to the strain that is in China. Does that matter clinically? And the answer is, I don't think anyone knows. I haven't been able to find any literature on it. Anecdotally, if you look at just mortality rates, the reported mortality rate in China is about 2.3%. And the reported the mortality rate coming out of Europe is all over the place. In Germany, it's as low as 1.2%, and in Italy, it's north of 10%. And that's really interesting because the strain that's in Germany and Italy is thought to actually be the same strain. And so that could be a function of comorbidities within the populations. That could be a function of age distribution within the populations. That could be a function of healthcare systems of the different countries, or it could be all of those combined, as well as genetic predispositions of those populations. Which of those, or if any of those matters, is unknown at this point, but really, really fascinating question. And I suspect that there will be a Love Goes Live on this in the coming weeks as somebody does that analysis and gets to that answer. Okay, let me stop sharing the screen. I hope I was cogent today. That's all I got for you guys. I found that really interesting and I couldn't stop thinking about it all day. Once again, my name is Mark Lubkowitz, rising from the ashes like the phoenix as always, trying to let crisis bring out the best in me. And stay tuned because next we're going to be looking at genetic variation of the ACE2 receptor. And does that lead to a genetic predisposition or susceptibility to COVID-19? Okay, see y'all soon.